Hello students, in this video we are going to talk about some relations. So basically we are going to study some relations between linear systems and linear equations. Yes, and we want to also know whether some basic linear equations has solutions or not. So first of all, I hope all of you remember what Picard's theorem is, right? So we are basing our study from there itself. So first of all, let's just start with some examples. Let's do some examples. See that, let's say we have an equation like this: y double prime plus a function of t, let's say a of t, times y prime plus b of t, right, times y equals to, let's say, c of t. Let's say that's the equation which is given to us, right? Yes, and I want to know, for now, for this lecture, let's just assume that a, b and c are sufficiently smooth. Okay, this is what we are assuming. Okay, sufficiently smooth. Now you see, the thing is sufficiently smooth. What I mean by this is, for now you can just assume there's c infinitely differentiable, right? No problem there. But the main point is this: we want to understand that whether, let's say, this problem has a solution or not. Question. Let's pose this question. Let's call this 1. Does 1 admit a solution? Okay, and of course for uniqueness you need to put a initial data. Yes, I hope that you remember. So for this problem, so let's say and does it have a unique solution? So does it first of all, it does add first of all, whether does it have a solution or not, and if it does, so, and whether it is unique, and whether it is unique, right? Unique. Clear? Now you see, the thing is, but for uniqueness, you need some initial data. Given an initial data, let's just put it in a bracket, given an initial data. Okay, so what that initial data may be, let us just write it down. So y prime, let's say at the point, for now let's just say 0 is alpha, and y at the point 0 is beta, or for now let's just call y at the point 0 is alpha and y prime at the point 0 is beta. Let's just call that. Yeah, now you see, to know whether this problem has a solution or not, okay, or it is unique given the initial data, we can of course change it to a system of equation. Yeah, so let's do that. See, for this problem what happens is, you can actually write it down in this sense that we will convert it to a system. So define a new function, right? Define v of t to be y prime of t. Clear? Yes. So once you do that, of course, if y prime is v, then y double prime is going to be v prime. Therefore, what we have is v prime is nothing but, from the equation, right, nothing but minus a t times v minus b t times y plus ct, right? This is what we have. See, now if you write it in terms of a system, we have, therefore, v prime y prime, clear, is equals to v times y plus c t 0. Okay, and y prime is nothing but v, so basically it is 1 0, and v prime is nothing but minus bt times y, right, and at times v, so it is 80 times v. Clear? Okay, now you see, if you define this thing as capital X, this thing as a of course depends on t, and this thing as your bt, then we can actually write it as x prime is nothing but 80 times x plus bt, right, plus the initial data. What is the initial data? Initial data is y at the point 0 is alpha, and y prime, which is v, at the point 0 is beta. So what is x at the point 0? It is nothing but v prime at the point 0, y prime at the point 0, that is v, okay, and y at the point 0, okay, which is given by alpha, which is given by beta and alpha, beta and alpha. I hope this is clear. I think it is correct also, right? X0 is this is x, right? So it is, sorry, this is x prime. So this is x. So v at the point 0, y at the point, yeah, fine. So you see, so and this is a vector in R2, yeah. So it's a 2x2 system, right? As I have always explained. Now you see, this is, so now whether this problem has a solution or not. So how does this problem looks like? This problem looks like this: x prime equals to at times x plus b of t. Okay, and x at the point 0 is given by some vector. Let's just call it x0. Yeah. So this is what it boils down to. So if we want to know whether one has a solution or not, we need to know whether this system has a solution or not. Let's just call this system as star. Okay. So does star have or admits a solution? So the problem boils down to this: admits a solution. If we know this, then we know that this sort of problem always has a solution. Yeah. So how do you get something like this? Okay. So let's understand this. And also the question is this: whether this problem is well posed or not. Yeah. Okay. See, this does it fall in this category? If x prime equals to f of x, x0 equals to x0. If it does, then we know that if f is c1, then all of this is done. But you see, star, let's call it double star. Okay, star is not a special case of double star, right? So basically what I am trying to tell you is this, that for a particular f, you cannot write it as f of x to be at ax plus bx, where a and b are variable, right? Yeah. So basically, see, the Picard existence and uniqueness theorem, which I did, that is for system which looks like double star. Okay, and we call this sort of system as an autonomous system. Okay, NOMOUS, autonomous system. Okay, and the thing is, autonomous systems are fairly easy to work around. So let's say that here in star, so as a special case, let me put it this way, as a special case, let's just think or assume that a of t is independent of t. So basically it is a constant a, and b of t is also a constant, let's say some b. So essentially what I mean is, you see here these coefficients are all constant coefficients, they are not variable. Yes, in that case, what can we say? See, in that case, at is a and bt is b. So therefore star turns out to be this sort of problem: x prime equals to ax plus b and x0 equals to x0. Yeah, and if you define, and if f of x equals to ax plus b, you do realize that f is going to be a c1. So this will imply this is in c1, right? This is c1. Yeah, and then you can use Picard's theorem, right? Of course we can do that in that case. Yes, but the thing is, if it is dependent on t, then we have to, so basically we need a Picard's theorem. So basically the thing is, we need a Picard's existence uniqueness theorem, that is existence uniqueness theorem. Okay, Picard existence uniqueness theorem for this sort of system: x prime equals to f of t comma x, x0 equals to x0. You see, if we know that there is a Picard existence uniqueness theorem for this sort of system, let's call this system as hash. Okay, if we know that there is a solution, existence of solution, and the solution is unique for the system hash, then what happens is, you can define f of tx to be at times x plus bt, right? And of course then you can use the Picard's existence uniqueness theorem to actually say that star has a unique solution in a neighborhood of 0, and which will actually imply that one will have a unique solution in a neighborhood of 0. Is this clear? Okay. So essentially the question boils down to this: can we say that Picard's existence and uniqueness theorem also is valid for a non-autonomous system? So this system, this sort of system is called non-autonomous system. Non-autonomous system. I hope this is clear, right? Okay. So for this, actually, we are in luck because Picard's existence and uniqueness theorem does hold. Okay. So let me put it this way. So first of all, let me put down the fact that what do we mean by a solution, and then we'll do it for this. Okay. So consider this system. Consider the non-autonomous differential equation, and what is differential equation? X prime t equals to f of t x at the point 0 is x naught. Okay, if you have this system, okay, first of all I want to find out what is the meaning of a solution. Okay, so by a solution, let's call this system as hash. Clear? So by a solution of hash, okay, we okay, let me rephrase this part. Yes, so basically we will say a solution of hash, system hash, right, is a differentiable curve, is a continuously differentiable curve. Let's just put it this way: continuously differentiable curve, okay, x of t, and where is it? In Rn. Clear? Defined for t in some interval, let's say I, okay, such that number 1, 0 is in I and x of 0 has to be x naught. Of course that should be true, right? So the solution which you are going to get should be defined in a neighborhood of 0. Clear? And number 2, for all t, right? So for all t of t, x of t must be in some omega. What is omega? I will define omega. So omega is a subset of R cross Rn, right? It's subset of open. So basically it's an open subset of R cross Rn, and we are going to define f from omega to Rn. Okay, so that is given. So we are starting out with the open subset of R cross Rn, and the vector field is given. So basically txt should be in omega. Clear? And x prime t has to be equals to f of t x of t for all t in I. Is this clear? So essentially you are given this system. Yeah. What is the requirement on f? So f is you see this t is varying in R kind of thing, right? So basically in some interval in R. So we can think of it as an R. So f is defined in R omega, which is a subset of R cross Rn. Here open subset, of course. This is open. Here, and you see we will also assume that it is continuous. So basically it means that it is continuous with respect to both the variables, the t variable and the x variable. Clear? Okay. So first of all, if there is a solution, that must exist in an interval containing 0, right? So minus epsilon plus epsilon some interval, and txt must always be in omega. Why? Because f of txt has to be defined, right? Okay, because f is defined in omega, right? And moreover, x of t must be equals to f of txt, and this should hold for all t in I. Clear? Then we call that as solution. Okay, so with that in mind, let's write down the local fundamental theorem. Okay, so this is local, again local fundamental theorem. You can also call it a Picard's theorem, it's not a problem. Fundamental theorem for non-autonomous system. Non-autonomous system. Okay, and what is the theorem says? Let's just look at it. So this theorem I am not going to prove it. First of all, the proof is exactly the same sort of proof which we did for autonomous system, just an extra variable t is there. Okay, so you have to modify it accordingly, but the thing is this is exactly the same, so I am not doing it. Please do it for yourself. You have to check that part. Okay, so what the theorem says? It says that let omega subset of R cross Rn, okay, be open, and capital F from omega to Rn is a C1 function with respect to x. We have seen, right, that you need f of x has to be c, so f has to be c1, because there in the earlier case it is just a function of x, so we need that same sort of thing. So it has to be c1 with respect to x. C1 means continuously differentiable, right? And with respect to t, what do we need? We need the very basic requirement. We just need continuity, and continuous with respect to t, right? Yes. Then if let's say t naught x naught is in omega, okay, there is an open set, then there is an open set, okay. Sorry, what am I writing? There is a small, let me put it this way. If 0 x naught is in omega, right, if 0 x naught is in omega, then there is an open set, okay, containing one second, if this set is there is it is C1, right, so you will have a unique solution. Okay, this is the open set I containing t and an unique solution, okay, of x prime equals to f of tx, okay, defined on I, okay, and satisfying x at the point 0 is x naught. See, 0 is just a, it doesn't have to be 0, it can be any t naught, doesn't really matter. Okay, I'm just writing it to be 0 just to make it look pretty, that's all. So essentially what I'm saying is this: if you have, right, so let's say this is the hash, this is what we have in question, right, this is the problem we have in question. It's a non-autonomous system. When can we say that there is a solution? Okay, so without going into all these details, so essentially what it means is, you see, f is a function of t and x, right? So with respect to t it has to be continuous, with respect to x1 it has to be at least c1, right? If that happens, then you will have a unique solution in a neighborhood of 0. That's what it is saying. To be very, if I'm not being very precise about it, this is what it is saying. So basically you have to remember this particular thing. Clear? Okay. Right? So if you want, I can just give you an example. Let's look at an example. See, one dimensional example, right? F of t x, and t is in interval, let's say minus epsilon to epsilon, okay, minus 1 to 1, or maybe r, doesn't matter. So let's say t is in r and x also is in r, okay, so x of t essentially. So now if I am taking f to be mod t plus x, right? Now you see what is your equation, and then the equation will look like this, right? That x prime equals to mod t plus x, and let's say x0 equals to some x naught, okay, x naught. It's a just an ODE, right? Now the question is this, whether this ODE has a solution or not. We can actually say that there is this unique solution in neighborhood of 0, because you see here this f, if you are writing this function with respect to just the t, yeah, this is continuous function. It is not C1, but it is continuous. And with respect to this, you do realize that it is going to be a continuously differentiable function. So this whole thing we can actually use in this sort of examples, that it is there is a solution. Or you can also look at this problem. Okay, then also you can say that all of this is true. Okay, so now as a corollary, what we can say is this. So let me put it as a corollary. So again, the proof, I am not doing it exactly the same sort of proof works what we did in the Picard's existence and units. You just have to have the single another extra variable, and you have to take care of that variable. It's not very difficult. Same sort of thing works. Okay, nothing special happening here. Okay, now as a corollary, let me put, and this is very important. Okay, please remember this thing. So let AT be a continuous family, okay, of n cross n systems. N cross n system, what it means is all the coefficients are basically continuous. That's what I am saying. All the entries are continuous functions. Okay, so let t naught x naught, clear? So let's say that is in some interval I cross Rn. T naught, if you are okay, so I will just put t naught. You can put it to be 0, doesn't matter. Then the initial value problem, what is the problem? X prime equals to AT times x, right? X at the point t naught is x naught, let's say. T naught can be 0 also, doesn't matter. Okay, so that has a unique solution on all of I. Okay, I hope this is clear. Right. So how do you prove something like this? Let's look at the proof of this. So without so first of all, you see, if you can show that it is continuous, I think this is, you can actually handle this proof. Okay, so how do you show something like this? Okay, so what we do is to see here what is f of tx. Okay, so see, I want you guys to check the proof of this. Okay, I will just give you an hint of how to do this. F of tx is nothing but AT times x. Clear? AT times x. Now you see this function here, a of t, it is a continuous family of n cross n systems. So with respect to this variable, this is continuous, right? And then again with respect to this variable, this is at least C1. Okay, so if that is true, then you have that f is actually going to be continuous, right? Yes, and f is continuous with respect to the t variable, and it is C1 with respect to the x variable. So we can use this local fundamental theorem for non-autonomous system, and hence we have a unique solution in a neighborhood of t naught. Clear? So this problem has a solution. Yeah? Right. Now this is not the end actually. So what you need to do is you have to show that the solution exists for all of I. You see, the solution exists for all of I. How do you prove something like that, that the solution exists for all of I? Okay, so this as a exercise, let me put it this way, exercise using Picard, using the let's call it star. Okay, using star, one has a local solution, right? Local solution. So basically t naught minus epsilon, t naught plus epsilon, there is a solution. But how do you extend that solution to all of I? Okay, but how does one extend the solution to all of I? Okay, I hope you understand. What is I? What is I? I, you see, is where a of t is defined. So t is varying in I, right? Okay. So what I am saying is this: wherever they are continuous. So basically, let's say a is continuous in whatever interval I. In that same interval, everywhere there is a unique solution. It doesn't have to be on a local. It's not local. Okay. This solution actually you can show that this is going to be global. Okay. Global means everywhere. Okay. See, the thing is, if you can show this, yeah. So this is an exercise. If you can do that, then we have already seen that any problem like 1, this problem, we have already seen that 1 can be written as a system, right, which is a non-autonomous system. It can be written as a non-autonomous system. So basically, if we can show that this non-autonomous system, you see this star non-autonomous system, if we can show that this star has a unique solution, clear, everywhere for all t, so basically wherever a and b are continuous, then you have a global unique solution. So basically, if there is a solution for this problem, so let's say a, b and c are continuous in some interval I, then you can say, and of course there is the initial data, you can say that you have a unique solution in the whole interval I. Clear? So this you have to do it yourself. So please check that part. Clear? So what is our summary of this whole video? In this video, what we have learned, and please remember, very important, given initial value problem. Okay, this is the initial value given to us. 1 admits. Okay, so let me put it in red. So we should remember this. 1, let's call it 2 plus 2. Okay, admits an unique solution. Admits an unique solution, okay, in I, and what is I? I is the interval where A, B, C are continuous. So basically the common interval where A, B, C are continuous, where A, B, C are continuous. Okay, so you do realize that just continuity of the the coefficients is enough to guarantee that there is a solution. Here, okay, so that is what we will just close our video with that comment.